We are now resuming our conversation. This is vaccination part 2. Okay, I think we have to take another break, but this is part 2 of this lecture in vaccination. Okay, so we are gonna switch to where we left off, and we were in the process of modifying the mathematical model. And we had done this. We had reduced the model that we had with 3 compartments into a model that has 2 compartments, such that now each of those state variables is a fraction. Okay, is a x of t is a number between 0 and 1. Y of t is also a number between 0 and 1. So now we no longer have 3 state variables. We have 2 state variables. We still have the same number of parameters. However, what we should keep in mind here is that these parameters have units, okay? And what we're going to discuss now is what to do to come up with a new form for the mathematical model such that the parameters do not have dimensions. We kind of get rid of the units. Here's where we're going to have some conversation on this. So we're first going to notice that the expressions that we had derived before, maybe I can write here on the side, we had x being a state variable. X is a function of t. Okay, so we were writing t as the variable for the time, denoting time units. That variable t would have, you can think of that variable as some specific units. It is time. So t may denote years or days or months or weeks. But you could even go into a finer scale. Okay, if I may. So here's, say, a representation of a section of the real line, right? So here's half of the real line from 0 to positive infinity. And you would think of t as taking values here, okay? Now, if we become very specific, then you can say, if the units of t are days, right? So then every mark that you have here, this is going to be 1, 2, this is 3, 4, and so on, right? Every mark there is one value for that time unit t, and this denotes days. But if you're interested in converting days to, and this is something that you should think of this. So say, for example, we want to convert from days into hours. So we know that one day has 24 hours, right? So that means that in every section here, we take a look at, say, between 0 and 1. Now there are 24 units. So we are going to think of dividing this into 1, 2, 3, 4, and so on. We're going to come back here with basically 24. This would be one step of 1 over 24. We'd come back with marks here that have length 1 over 24. Okay, and that's because we are taking some resolution of that unit, and we're now specifying that we want more subunits within that interval. Okay, so that's the idea of thinking of still time, but one thing is to represent time in days, another thing is to represent time in hours. Imagine if now instead of days you're going to represent this into seconds. Okay, so one day has 24 hours, 1 hour has 60 seconds. 1 hour has 60 minutes and 1 minute has 60 seconds, right? So the more resolution, the smaller the unit, then you're going to end up with more points within that subinterval, okay? So with that idea, suppose that now you're interested on considering a different time unit, okay? So we have, basically what we're writing here is that let t be equal to some constant c times tau. Okay, I know those symbols t and tau look a little similar when I write them by hand, but this says think of the variable t as a constant multiple of another variable that we call tau, and both t and tau are measuring time. Okay, so again, if you think of a year, think of a year as a multiple of minutes. How many minutes there are in a year, right? So you can write 1 year equals to this amount of minutes, right? So this is the idea of having conversion, if you will, between one unit of time versus another unit of time. Think of 1 unit of time, t, as a constant multiple. So here, this term is a constant, okay? And it so happens that that constant, the multiple that multiplies tau, it so happens that that constant is no stranger here. It's no stranger because basically, remember when we wrote the equations for the infectious class, right? The infectious class, here is the infectious class, here is I. And basically there were two ways of getting out of I. One way is that you would go under gamma I at a constant rate of gamma. That means you were being transferred from infected to recovered. Another way out of I was mu I by dying due to some, not necessarily due to disease, but by dying. So because these are the constant rates at which you may get out of this compartment, then there's a standard calculation that says that 1 over gamma plus mu, this is the average length of time that one individual spends on that compartment I. So this is something typically called the infectious period. The infectious period is the length of time, okay, average length of time spent on that compartment I. And so you can see how this constant is precisely the constant that we are writing there as the constant, the multiple of the constant that multiplies tau. So this is thinking now as one time variable in terms of a constant multiple where that constant is the infectious period, okay? So what we do is that we define a new variable of time, and this is how we relate the old variable to the new variable. We relate them by this expression here, okay? So t equals the infectious period times tau. Maybe I delete this, make it some room, okay? And so if that is the case, that means that when differentiating with respect to tau, when differentiating, taking the derivative of t with respect to tau, that means we will be taking the derivative of this right-hand side with respect to tau. This infectious period is a constant, and the derivative of tau with respect to tau is 1, right? So this here simply is 1 over gamma plus mu, which is a constant, is the infectious period. Now, the state variable x is a function of t, okay? But that t is a function itself. X is a function of t. However, t is itself a function of tau. Okay, so we are making a relationship between the time variable t and the new time variable tau, and that relationship is due to this multiplying by this constant, which is the infectious period. This means that if we're interested on the derivative of x with respect to the new time variable tau, that means we're differentiating with respect to tau x of t, which itself is a function of tau. So you may see what's going on here. We're differentiating with respect to tau, and to do that, we have to differentiate x, which itself is a function of t, and t is also a function of tau. Okay, so this is something that if you're having flashbacks, then that's a great thing, because the way in which we compute this derivative to the innermost, the variable that is most in this composition, the variable that is inside the innermost variable, to do that, we invoke your old friend, the chain rule. This is a good friend of yours. The chain rule from calculus 1. So this means that this is dx with respect to t times dt with respect to tau. Okay, so please, I want to be precise, and I want to emphasize that this calculation is now with respect to, this is the derivative of the derivative of x with respect to tau, that is equal to the derivative of x with respect to t times the derivative of t with respect to tau. Okay, so let's proceed. So basically, we have an expression for dx dt, right? And we know that we already calculated this, that the derivative of t with the derivative of t with respect to tau is equal to a constant. So let's put both of those things together. Okay, so here we have dx dt. Okay, dx dt is 1 minus p times mu minus beta times x times y minus mu x. Okay, remember this here is nothing else other than dx, the derivative of x with respect to t. And then we're multiplying that times 1 over gamma plus mu, because that portion there, this here, is the derivative of t with respect to tau. Okay, so this means that we can multiply that constant. So this is 1 minus p times mu over gamma plus mu minus beta over gamma plus mu times x times y minus mu over gamma plus mu times x. That's what this expression is looking like. So remember, this is all dx dt. Dx dt is taking this form, and so now we're going to introduce some variables. Remember, this is something we had actually learned how to compute this quantity by using the next generation matrix. Next generation matrix for the SIR model with births and deaths, even with this new form with vaccination, the matrix is basically 1 by 1. So this is what we know as the basic reproductive number. Okay, the basic reproductive number. Now, this is defined for this model as beta, the transmission rate, divided by gamma plus mu. Let me write this again. This is beta times 1 over gamma plus mu. In other words, this is the transmission rate multiplied by the infectious period. Okay, and so what I want to emphasize now is what are the units? What are the units? So beta has units of time over, maybe write this. Beta has units of 1 over time, and the infectious period has units of time. So that means that the units of R0, right? That means that the units of R0 cancel. Why is this true? Well, think beta could be something like 2, you'd say 2 over day. If this is something like 2 over day, this means 2 per day. This has the meaning of saying there are 2 transmissions for each day. Every 24 hours, there is a transmission of 2. Okay, there is a possibility of passing on 2 or 3 or 5 or 1.7, whatever this number is. Okay, but the units of this number are in terms of units of time. This is a rate. Okay, this is a rate, meaning that you have a number per unit of time. So this is a number per unit of time. Okay, and because this is the nature of this parameter, then we're gonna have that the units of beta are always time to the minus 1 or 1 over time, and therefore the units of R0 are canceling. 1 over time times the length of time when an individual is infected that has units time, right? So they cancel each other. So that means that R0 has units, has no units. Okay, now let's comment on this other quantity. This is 1 over gamma plus mu. This is an infectious period, and this is multiplied by mu, but I'm going to write actually mu as 1 over mu. Okay, and I'm doing this because now we can actually interpret this expression as a ratio, something that is dividing by 1 over mu, and what we're dividing by 1 over mu is 1 over gamma plus mu. And what's the point of doing this? Well, the point of doing this is that we would be comparing the infectious period, which when we discuss the calculation of the reproductive number, the basic reproductive number, we talk about the next generation matrix, and we talk about how that matrix is an operator that keeps track of the secondary infections, right? So we're thinking with that methodology as in terms of the infection process, in where the gains or arrivals for the infections are offspring, how the infected individuals are capable of yielding offspring, and the departures out of that infected state are not necessarily meaning natural death or death due to infection, but simply is that individuals are no longer capable of passing on the infection, right? So there was already a notion in that when we discussed that method of the generation, the generations, thinking of that process as somehow as a branching process, and now how in time scales of generations of the infection as they relate to the offspring of infection. So 1 over gamma plus mu is a length of time with some time units, and that is a length of time for how long an individual remains infected on average. Now the ratio 1 over mu, this is the average amount of time an individual is in the population. Okay, so 1 over mu is what we call the life expectancy. The life expectancy is the average number of time, is the average length of time an individual is alive in this population. So remember that there are departures out of every compartment. Individuals depart at a constant rate mu. Mu denotes the rate at which individuals depart the compartment called susceptible, depart from infected, or depart from R. So mu denotes a rate of death due to natural causes, okay? And that means that 1 over mu is the average length of time individuals are in this population, this closed population. So that average length of time is what we call life expectancy. So what's this new parameter f here is comparing the length of infection divided by the length of time an individual is in this population. Okay, just to give you an idea, think of life expectancy as something like, I don't know, 70 years. Okay, 70 years. And think of the length of infection as some diseases have an infectious period of 1 day. Some diseases have an infectious period of 7 days. If you are infected for 14 days, for 2 weeks, or for even a month, that's possibly very, very remarkable. But even so, a month, 4 weeks, 2 weeks, 1 week, when compared to the life expectancy, you're comparing days or weeks over many years, over 7 decades, over 80 decades. Think of, this F. Think of this F. If you want to throw in some numbers there, think about somebody that lives for 100 years, and then maybe they have an infection that lasts 10 days. Right, so this is a ratio here. You have to convert days to years, but then both, this is a ratio of time of infection versus time of being alive in that population. Okay, and all this to say that this new parameter F is a parameter that has also no units. Like R0, F is a parameter which is defined in terms of ratio in which the units cancel with each other. Okay, so what we do now is that we use these new parameters. Remember, in that expression that we had derived, so here we have beta over gamma plus mu. We could substitute this with R0, and this is the other expression that we end up here, which is also repeated in here, and we can call this F. So we can rewrite this equation. This is the derivative of the fraction of susceptible individuals now with respect to the new time variable tau. And this derivative now reads as 1 over p times f minus r0 times x plus y minus fx. Okay? So turns out we can do something very similar with the other expression in our model. And again, remember that now we are interested on differentiating with respect to tau. So basically we have that y is a function of t and also t is a function of tau. So when we're doing this calculation, we want the derivative of y with respect to tau. This is going to be the derivative of y with respect to t due to the chain rule times the derivative of t with respect to tau. Okay, so and what is this equal to? Well, the derivative of y with respect to t, let's write that expression. This will be beta xy minus gamma plus mu times y, and the derivative of t with respect to tau is 1 over gamma plus mu. So this becomes beta over gamma plus mu times xy minus gamma plus mu over gamma plus mu times y. Okay, so this start to look like this would be r0 times xy minus gamma plus mu cancel with each other, and then this would be minus y. Remember, this is the derivative of y with respect to the new time variable, which we call tau. Okay, so that means that we can rewrite the system. We have reduced the system from 3 differential equations into 2 differential equations. These state variables x and y are fractions, so they're both between 0 and 1. And we have also changed time units. We have defined a new time variable such that now we have derivatives with respect to tau and not with respect to t as our original model. And now this model has parameters p, r0, and f. Okay, so we have reduced the model into 2 equations, and now we have only 3 parameters. Okay, and here r0 is a very meaningful parameter. R0 denotes what we call the basic reproductive number, and we have discussed this number at length, average number of secondary infections that are produced by an initial infected individual into a population that is completely naive, that is an entire susceptible population. Okay, so what we're going to do last is that we're going to simulate this model. We're going to discuss some numerical solutions for this model. So we're going to take a little break here, and we will resume shortly.